Hello, Honors Physics students. Okay, so you just finished going over all the data and all the connections and all the patterns you saw in the data from the lab for series of parallel connections of resistors. You developed some equations for it, and now we're going to put it all together. So I want you to take out the notes page where a lot of this is already filled in for you, but then we'll fill in some other things together. So we'll do a side-by-side comparison of series and parallel, and really one of the big differences is in the number of paths. And so if you go back to here in our notes, where you drew all the circuit diagrams, let's look at C and D, which are our pure series connections. How many paths are there to get around? Well, even though there's two resistors, there's only one way to get around. In D here, there's 1, 2, 3, 4, 5, 6, 7 resistors, but there's only one path to get around. This, of course, brings up the idea of the resistors being dependent on each other. This is why if you take one out, all of the rest of them will go out, or all the rest of them will stop working because there's only one path. You've broken the single path. Letters A and F, though, are pure parallel connections. Here is where the wires are joined together, our junction. Conjunction, junction. What's your function? That's right, Schoolhouse Rock, still alive. Alright, good. Anyway, so here's where the wires are joined together, where the charges have a choice, either this path or this path. And since there are these alternate paths, that's where if you take one out, the other one will stay working. They're on these separate, independent branches from each other. There's multiple paths to get around. Here, there's 1, 2, 3, 4, 5, 6 different paths to get around. That makes it a parallel connection. Okay, so here is our series description. Just one path. Each depends on the other. If it goes through one, it must go through the next. And this is what I was saying before, is that really is probably the strongest way of telling if resistors are in series. If the charge goes through one resistor, and then it must go through something else before proceeding on its way, they must be in some sort of series connection. Now for parallel, this is where we have the multiple paths, that's the junction you see on the circuit diagram, the choices for charges to make, and they're each independent of the others. So what are the consequences of being in series or parallel? Well, in series, with only one path, this is why the currents have to be the same. If there's only one path, where else will the charges go, right? Every charge that enters one resistor and then exits on the other side has to enter the next, has to enter the next, has to enter the next, because there's nowhere else for them to go. Currents, of course, measure charge per time. And so, since the charges all go around at pretty much the same speed, they're all flowing around together, the rate of charges entering and exiting any given resistor is going to be the same because there's nowhere else for them to go. However, in parallel, we know that at the junction, the charges split up, which means the currents split up. That's where it said I total equals I1 plus I2 plus so on and so on and so forth, that when the charges get to the junction, they split. Some charges go one way, some charges go the other way, and they come back together at the junction on the other side. But the current splits at a junction. But that tells us that the voltages have to be the same. From our conservation of energy idea, whatever the charges gain in voltage through the battery, they have to lose somewhere else through the resistor. And if there are multiple paths, and let's say there's only one resistor in each path as there was in the lab, well then no matter which path it goes on, it has to have the same voltage drop. Now, it's not always going to be such a simple combination like that, but yes, anytime resistors are in parallel, the voltage drops across them have to be the same. Or really, any branches in parallel, the total voltage drops have to be the same. That's not the same as in series. Because there's only one path, when a charge goes through one resistor and then goes through the next and goes to the next before coming back to the battery, the voltage drops are split among those resistors. It can't possibly lose all the voltage through any one of those resistors because then there's no more energy. That's what voltage measures, right? There's no more energy to be lost through the other resistors. That's just not how it works. So the voltages are split among the resistors. That's where we had delta VB equals delta V1 plus delta V2 and so on and so forth. Okay, now let's talk about equivalent resistance. When you put more resistors in a series combination, what happens to REQ? Well, the equation shows it. REQ equals R1 plus R2 and so on and so forth. And you did it with the lab. You had 10 ohms and 5 ohms, and together they made 15 ohms. That means you got a larger REQ. So REQ is larger than any of the individual resistors. That kind of makes sense, right? You're putting more resistors in the path, putting more impediments to the flow of the charge. What about in parallel? When you put more resistors in parallel, what happens to the overall resistance, the equivalent resistance? Well, you did it here as well, right? You had the 10 and you had the 5, and you took the inverse of them and added them back together and took the inverse at the end, and you got 3.33. That was the ideal equivalent resistance for the circuits. So you had a 5 and a 10, and REQ was 3.33. That means you actually got a smaller REQ when you put more resistors in. Well, this seems counterintuitive, doesn't it, right? You're putting more things there. Why are we getting a smaller REQ? Well, to explain it, let's go back to our ski resort analogy. All right, so let's say you're the owner of the ski resort. It's a beautiful day, but not a whole lot of crowds there. So you get there in the beginning of business day, not a whole lot of people there. You only open 2 trails. You have the Black Diamond and the Bunny Slope. Okay, so people are going along there. People are happy, but it's a beautiful day. And this is, social distancing is out the window. It's a normal day. And so the crowds start getting larger and larger. The lines get longer and longer. And the people are getting more and more upset because they've got to wait longer and longer to go on the trails. So as the owner of the mountain, what do you get to do? Well, open up more trails, right? The more trails that are open, the more chances these people have of going down the trail, and they can flow more easily. More opportunities, more people move, there's a larger current. These more opportunities represent the branches in parallel. The more options the charges have, the more charges can flow. If the current goes up, the overall resistance goes down. Okay. Let's look in a little more detail at the resistors in parallel. So here we're going to turn to our problem set, and let's look at problem 19. Go ahead and read it. So the equation we developed by looking at the data and doing the algebraic manipulations was this one here, of course, 1 over REQ equals 1 over R1 plus 1 over R2. And of course, in reality, this keeps going, but 1 over R3, 1 over R4, and so on and so forth. But let's take the example of just 2 resistors in parallel. Because if there's just 2 resistors in parallel, let's see if we can just do a quick algebraic rearrangement of this to have a little bit of a shortcut, so we don't have to keep doing our 1 over X button on our calculator or X to the minus 1 button on our calculator like we did when we did our lenses and mirrors. Alright, so just pause the video here, do your algebra magic, solve for REQ. Okay, this is, way easy. It's definitely below the sort of challenge I usually give you here. We're adding fractions. What do you do when you add fractions? You get a common denominator, of course, right? And so what's the common denominator you can get here? We don't even know the numbers. It's just the product of the two. So it's going to be R1, R2, and R1, R2. The left-hand fraction multiplied by R2 over R2. The right-hand multiplied by R1 over R1. And so here we have, right? And now what do? We just add fractions, right? Nothing fancy here. Got a common denominator. So the top is R1 plus R2. Notice I did flip the order of these. Ooh, that's not really that fancy. I just did that to make it look a little bit nicer. Put them in the correct order. This is nice, except this still is 1 over REQ. This still is not our actual answer, right? We want REQ, not 1 over REQ. So what do? Well, the hard way to do it would be to cross multiply. The easier way is just say, well, look, this is 1 over REQ. We want the inverse of that, which means you just take the inverse of the other side as well. In other words, flip them both over, and we get this. REQ equals R1 R2 over R1 plus R2, or as I like to say it, the product over the sum. This is a really nice little shortcut, and so we're going to go ahead and make it not a full-fledged new equation, but a quasi-new equation with our stipulation, our warning, when to use it, right? We can only use it for 2 resistors and only when they're in parallel. I mean, if they're in series, we don't have to go through all of this. We just add them up. That's easy. Don't be ridiculous, right? But it's only for 2 resistors in parallel. It doesn't keep going. If you did 1 over R3, 1 over R4, and so on and so forth, and try to get a common denominator, the algebra gets really, really complicated very quickly. So this is not just on the top R1, R2, R3, R4, on the bottom R1 plus R2 plus R3 plus R4. No, that's not how it works. Feel free to try it on your own and you'll see it's not nice. But for 2 resistors, it is nice. And this is often the sort of thing that if you don't even need a calculator to do. The numbers are really easy. Sometimes you can just do the product in your head and the sum in your head. Maybe then you need a calculator to do the division, but a lot of times you don't. And so like on a multiple choice question where you don't really want to spend a whole lot of time showing all your work and punching numbers in your calculator, if you can do this in your head, that just makes your life a lot easier. And that's what we are always going for, making your life easier.